Problem number 49, we have a double integral with the limits of integration already set up for us, so it's just the process of running through the mechanics of a double integral. So it goes dy dx, so we integrate respect to y first. There are no other y terms, so that's going to produce a y right here, and then cos of 5x and 0, which will just leave a cos of 5x. So now we have the integral from 0 to pi over 10, sine 5x, cos 5x. And that's just straight u substitution, nothing too fancy there. Let u equals sine of 5x, and of course with the chain rule, the derivative is 5 cos of 5x. Now I didn't show the next step, which would be 1/5 du equals cos of 5x, so there's the 1/5 right there. And I like to change the limits of integration, so I don't have to go back to my original variable again. So if I put in pi over 10 here for x, I'll have sine of pi over 2, which is 1. Put in 0, sine of 0 is 0. So now all we have to integrate is 1/5, 0 to 1, u du, and it's pretty easy from there. So then 1/2 u squared makes it 1/10, put in 1, put in 0, and we get 1 over 10. So that wasn't too bad. Let's look at another one here, number 50. 50 is also going dy dx with no y variable here. So the antiderivative dy just produces a y. We bring in a 4 minus x squared and a 0. So of course 0 won't affect anything, but 4 minus x squared goes in for y. Multiply it by x, you'll get 4x minus x cubed. And then we integrate that from 0 to 2. So the antiderivative of 4x would be 2x squared. And then antiderivative of x cubed will be 1/4 x to the 4th. Put in 2, put in 0, and you'll end up with 4 as the answer. All right, so that's not too bad. Let's jump down here. Now this one we're not going to integrate. We're just going to set up the region. And this is where I think the graph is pretty much needed. So let's see what we got here. Oh. So it wants to set up the correct region, integral for this region of integration bounded by these graphs. So all the answers are dy dx, and it's telling you it wants dy dx, so we don't have to do the other order. And let's see. So there's, you can use a graphing calculator to do this. I just did a rough sketch manually. So dy dx will only require one integral because it's the same lower and same upper. Actually, if this was dx dy, you would have to set up two double integrals to add them together, because you'd have two different functions on the right there. So you'd have to cut it off right across the middle and then do left to right and then left to right and add them together. So this is the easier way to do it anyway, thank goodness. So dy dx, lower to upper. So y is a function of x, so lower to upper goes x to 20 minus x squared right here. And then, you can use the calculator to get the points of intersection if you'd like. But it's easy to do algebraically. Set them equal to each other. Factor beautifully. You get -5 over here, +4 here for x. So then it goes from -5 to 4 on the outside limits. And that will be answer A. Let's see. Here's one where we have to reverse the order of integration. Let's see. So once again, I graphed. So y is going from 22 minus x to 15. So there's a line 22 minus x coming in there, like so. And then, of course, y equals 15 is a horizontal line. So, you got to figure out. And then the outside limits x are going from 7 to 15 right here. So it's trapped here on the x-axis by 15. That's, but it's definitely this region right here, to put it between those two y curves, is right there, and then this right vertical line is what stops it from keep going there, so that keeps it bounded. So that triangle would absolutely be our region of integration. So if y equals 22 minus x, then x equals 22 minus y, because now, of course, when we reverse the order, we have to solve for x in terms of y. So now, since we're going dx dy, to read this from left to right, we're reading it from 22 minus y, which is the angled line, and then the right x will be 15. So it goes from 22 minus y to 15, left to right, so there's 22 minus y to 15, and then vertically we're going from 7 to 15 for y. Because obviously when you put 15 in there, you're going to get 7. If you put 15 for x into this equation, y will be 7. That's why I drew that 7 in there also. And then there we are. We have it. It will be right here. Answer B. Now here's another change the order and then evaluate. We'll see what we have here. Let's get the region all taken care of here. So x equals y squared is a sideways parabola. Probably wouldn't hurt to know that, but if you didn't, you could just take x equals y squared and solve y as plus and minus the square root of x, and graph those as two separate equations, and then it would do each half of the parabola that way, like so. And then we have a vertical line, then x equals 1. And then the fact that y has a region from 0 to 1, that's what makes it the top part of this, is the y boundaries. So let's reverse this around and see what happens. So we got to obviously change the equation around. So if did I write that anywhere? Well, I did when I solved it here. But anyway, let me mention it verbally. So if y squared equals x, that means y would equal the square root of x. And like I said a minute ago, it's plus and minus square root of x, yes, for each half. But because the shaded region is only in the upper half, we just need the square root of the positive square root of x. So to interpret this as dy dx, we're going vertically first. So we're going from 0 to the square root of x right there. And then 0 to 1 on the x-axis. All right. Since y equals the square root of x, that means whenever, x is 1, y will be 1. So they just both happen to be 1 right here. All right. Let's see. So there's how I got this set up. And so the first integral is with respect to y. So we can leave the 1 over 1 plus x squared alone, like I did right there. And then the antiderivative of y would be 1/2 y squared. So I just tossed the 1/2 out to the outside. And then, so the square root of x squared becomes x. And now I have this integral. Of course, once you get these integrals down to the final integral, I can't really stop you from doing it numerically in a calculator, which is fine. That's okay. But I like, showing the work on how to do them. I think it's a good skill to know. But anyway, you got this integral. I guess you could go right to the calculator. And of course, then you would have to, though, convert your answers choices. If they're like the answer choices here, you'd have to convert them to decimal, because your calculator is not going to show these answers. It would show the decimal equivalent. In fact, I guess I could put that in there in a minute here and show you. Let me bring up. Bring up my calculator. Let that warm up. Back to this. Anyway, so it's a straight u substitution. You just let u equal 1 plus x squared. Du equals 2 dx. I didn't bother to write the 1/2 du, but same thing as that other problem. So there's the 1/2 when you divide both sides by 2. And then I change the limits of integration. So if you put 1 into here, 1 plus 1 squared will be 2. You put in 0, 1 plus 0 will be 1. And then see, we already had a 1/2, excuse me, that came from the y squared over 2. When I said this was a 1/2, I was pointing at the wrong place, my mistake. That 1/2's already there. This new 1/2 comes from dividing both sides by 2 right here. So there's two 1/2s. So then we have 1/4, the integral from 1 to 2 du over u, and which is 1/4 natural log of u. Put in 2, put in 1. Actually, natural log of 1 is 0, so that's why there's nothing else here. So that's 0, so it's just 1/4 natural log of 2. So if we put that integral in there, and, oh, I forgot I can just add the 1/2 at the end. So it was x, then, divided by, better put parentheses here, 1 plus x squared, close parentheses, dx, and then I guess, like I said, let's check here. Yeah, there's 1/2. So I'll put times 0.5. And then now I'm going to go 1/4 times ln of 2. And they match. So you would, have to calculate the answer choices. No one would expect you to recognize that 1/4 ln of 2 equaled that number, but so you try them out, see which one you might get lucky. It might be first answer you try, or it might be the last answer you try. But all right, so that takes care of that one. Let's look at number 54. We're going to change this to polar. All right, so this is going to be a circle with radius 5. And because basically we have y equals square root of 25 minus x squared, which is the same thing as x squared plus y squared equals 25. But the important thing to determine here is we have to know how much of the circle is it. These problems can be quarter circle, half circle, full circle. And because both the y and the x have negative, they're not cut off by zeros. They both have the negatives here. We're absolutely covering the entire circle. So the 0 to 5 would have been the same no matter if we were how much of the circle we were including, because the radius of the circle would be 5. But where that affects your answer is right out here on these outer limits. So since it's the full circle, that would be 0 to 2 pi. And so there, the limits of integration are now set. So we're going to convert this to polar. X squared plus y squared will be r squared. So it's 1 over 1 plus r squared squared. And then always remember, when you convert from dy dx to polar, there's always that r in there. So it goes r dr d theta. So the r is always there. And the r is actually very important because that's what's going to make this integral become, u substitution. So you let u equal 1 plus r squared, du is 2r dr, so divide both sides by 2. So it puts a 1/2 out here. And I change my limits of integration for the first integral. I'm certainly not going to need to for the second integral. So you put in 5, 1 plus 5 squared is 26, 1 plus 0 squared is 1. So this is u squared on bottom, so when you bring it up, it's u to the negative 2. So it's u to the negative 2 du from 1 to 26 is the integral we're going to evaluate right now. Okay, that's not natural log. It's only natural log when it's the first power on bottom. U to the 1. But so u to the negative 2 is just power rule. I didn't write out the details, but it's basically the antiderivative of u to the negative 2 is u to the negative 1 over negative 1. So it's 1 over u. And then it produces a negative, so it just changes that to negative 1/2. So now, so we put in 26 and we put in 1. Now what okay, let me mention this now because I didn't actually write that out when I did this. I just sort of did it on instinct, I guess. But there's a property of definite integrals back from Cal 1 that says, you know, if you reverse the order of the limits of integration, that creates a negative. So in this case, I wanted to create a negative to get rid of that negative. I just figure the fewer negatives you got hanging around, the least likely there is to make a mistake. So actually, when I came over to this part, I put in the 1 first and not the 26. So I'll put in the 1 first, so 1 over 1 makes 1 right there, then the 26. And then now that changes to positive. So that makes basically it's 26, makes that inside part 25 over 26 times 1/2 gives you 25 over 52. And then the antiderivative of d theta from 0 to 2 pi, that's easy enough. That just gives you theta. So it's just going to throw a 2 pi in there. So the 2 pi comes in, and then the 2 reduces the 52 to 26. So it ends up being 25 over 26 pi, which is answer D. Excellent. Let's take a look at this number 55. All right. Another polar. Now I kind of drew a sketch of the region. I didn't draw it for the other one, I guess, but it's okay. It was just a full circle. But this one, because we're limited at both lower bounds at 0, we're only in the first octant. So that just gives us quarter circles. That's how we know it's going to be 0 to pi over 2. When they're both zeros, that will always be true. Didn't mean to draw that. And let's see. So the x squared plus y squared will be r squared, of course. And tired of leaving random dots there, so I'm going to switch to this symbol. Unless I need to sketch something. So that x squared plus y squared gives you r squared. Then we have the automatic r dr d theta. So that's not a very difficult integral involving e. It's just u substitution. So we have u equals negative r squared, which makes du negative 2r dr. So that brings out a negative 1/2 on the outside. And then u of 4, put 4 in there. Now keep in mind this isn't in parentheses, so it's the negative of 4 squared. So it's negative 16. Not positive 16. That's a very common mistake. And of course, 0 will be 0. So now we're evaluating, so negative 1/2 e to the u. Negative 16 on top, 0 on bottom. I didn't write this step out, but I did the same thing as in the last problem where I reversed them to get rid of the negative. So actually I put the 0 first. So e to the 0 would be 1. Then I put in the negative 16 second. So I have e to the negative 16 here. And then so I have 1/2, and then that's just a constant right there, 1 minus e to the negative 16 d theta. So that brings in so the antiderivative d theta is theta. That's just going to drop a pi over 2 in there. So 1/2 times pi over 2 makes pi over 4. So we have pi over 4, 1 minus e to the minus 16. And there it is, answer A. Surface area, number 56. We're going to find the surface area of the part of that plane that's lying in the first octant. So let's see what we have. Now, I didn't write the surface area formula down there, but it's the square root. You're integrating the square root of 1 plus fx squared plus fy squared, or z, whatever. So you want to have the surface area formula written down, or if I've provided it. If you're using note sheets at the time of this video, then I would not have provided it. But if I go back to providing the formulas, then you'd have it. So I want this video to cover both scenarios. At the time of this recording, you're using a note sheet, so you can put it on there yourself. So let's see. We have to solve this in terms of z, so we can get the x partial and the y partial. And this one's very easy. So you would get z equals 16 minus 3x minus 6y, which gives me a partial of negative 3 for the x partial, and negative 6 for the y partial. So actually there's no variables here. That makes the integral actually very simple. Because if you end up just with a constant here, so it's just going to be 1 plus 9 plus 36, which gives you the square root of 46. Now to find the... Now we have to figure out what region we're integrating across. And we're integrating across the base in quadrant 1. So we can solve for this bottom part. I got that z-intercept, even though we didn't need it. To get the z-intercept, you would put in 0 for x and y. So it just gives you a height of 16. All we really need is the base. So the base equation on the xy plane means z is 0. So our region of integration is going to be 3x plus 6y equals 16. So now it's a matter of whether you choose to go dy dx or dx dy. I realize there are some situations where that matters, but it does not. In this particular case, it doesn't. I think, in other words, one way doesn't necessarily make it easier than the other. So I chose to go dy dx. In that case, that means I have to solve for y in terms of variable x. So you take this, solve for y in terms of x, you get 1/6 times 16 minus 3x. And then remember, the outside limits are always numerical. So then all I need is to find is the x-intercept. So I put 0 in there for y, which gives me 3x equals 16, x equals 16 thirds. And so there we go. We have 0 to the 1/6, 16 minus 3x dy, and then 0, 16 over 3 dx, and the square root of 46 is the function we're integrating. So the antiderivative dy would just be y. So it throws in this, so when you drop in the 1/6, 16 minus 3x, I went ahead and just immediately in one step put the 1/6 to the outside, which is perfectly fine, along with that square root of 46. Just leave that sitting out there. And then we're just integrating 16 minus 3x with respect to x. So that's going to be 16x minus 3/2 x squared. And now we put in 16 over 3, put in 0. I kind of did all this manually, but like I said, you're probably going to want to use a calculator to do this. So yeah, I put them in there. 16 times 16 over 3 is 256 over 3. 16 over 3 squared is 256 over 9. So 3 over 9 is 1/3. And then I got a common denominator of 6. So that makes 256 over 3 be the same thing as 512 over 6. And made that 256 over 6 and started reducing fractions again, and finally got down to a simplified answer. Once again, you can just get the decimal answer if you wanted to and just figure out which answer is correct from there once you get it down to the final integral, once it's down to one variable. But I actually, worked through it and got a precise answer here. Let's see. So it is answer D. 64 over 9 times the square root of 46. Now this one is just setting up the integral for the surface area without evaluating. All right, so it's already set up for us, this paraboloid. Z is already isolated, so we can take the partials as is, which will be the x partial will be negative 2x. The y partial will be negative 2y. So then we have the square root of 1 plus 4x squared plus 4y squared, which I kind of gives away the answer to this problem, doesn't it? Now, as I'm mentioning here, the way they did it here is fine. But they're using a multiple of 4, and then they're just putting it in the first octant and then just multiplying it by 4 to cover the entire circle. That would be the same thing as if they left the 4 out and put the negative square root of 9 minus x squared on bottom and the negative 3 on bottom. That's a little weird, but it's okay. So that's what I'm mentioning over here. See, it's quarter circle, and then the 4 gives it the whole circle. And then there's what it would be without the 4, which is probably what most people would normally do. And you can integrate this one fairly easily in polar coordinates, although it was not asking that here, but it would not be difficult. I just want to mention that. You would have the square root of 1 plus 4r squared underneath there, and then you would have r d theta, and it would be an easy u substitution. I'm sure I have problems like this in my notes, a problem like this, and then you would just be going from, r would be going from 0 to 3, and then you would be going from 0 to 2 pi on the outside without having to mess with that 4. So, okay. I find that a little weird. They chose the way to do it with the 4 there, but that's all right. Volume. Okay. So technically this problem, I guess this problems aren't in exact order, content, because technically this section was before the surface area until you get to volumes involving triple integrals, but that's okay. They're kind of grouped together by course content, so it's not, this is an example that they're not in perfect order. So now we got that paraboloid again, so this time we're just trying to find volume. So I didn't draw a picture here, but you see it just says, so when there are no restrictions, where it doesn't say like x greater than or equal to 0 and or y greater than or equal to 0 or stuff like that, you assume it's the entire circle unless told otherwise. So it would be. So this is basically the base of the paraboloid is going to be x squared plus y squared equals 9. So that's our region of integration. So I didn't sketch out the circle or anything, but x squared plus y squared equals 9. So it's going to go from 0 to 3 and then 0 to 2 pi around the entire circle. And so we have 9 minus r squared. And then, of course, you have r d theta when you set it up in polar. Now, you could do u substitution here, and which I would absolutely be doing if the exponent around this parentheses was a fractional because it was a radical or raised to a higher power, like second or third power. But whenever parentheses are to the first power, you also have the option of just distributing through the parentheses. You can't multiply if it's through there if there's any power other than 1. So what I did here, even though I sort of looked like I left out a step, but I'll explain that step right now, is I distributed, then took the antiderivative. So 9 times r, and that antiderivative would be 9 halves r squared, and then I'm going negative r squared times r, which is negative r cubed. So that antiderivative then would be negative 1/4 r to the 4th. And yeah, so that's what I did. I distributed this time, but if you would have done U substitution, correctly, that would have been fine. That would have been okay. But I didn't feel the need for it here. So put in 3, put in 0, and I got 81 over 2 minus 81 over 4, which happens to be 81 over 4 because this will translate to 162 over the 4. 81 over 4, 0 to 2 pi, d theta. Antiderivative is theta. 81 over 4 times 2 pi is 81 over 2 times pi. And there we go. Okay, that wasn't too bad for a double integral volume. Number 59, we got to evaluate a triple integral. Let's see what we have. So I would go dz, dy, dx because you got both variables y and z here. I guess you could go dy, dz, dx, but definitely want x to be last because x is clearly numerical here. But if I go z first, that means I got to solve for z in terms of what are the variables there. So z equals 2 minus y. So to go from 0 to 2 minus y, and then y would go from 0 to 2. Because if you put in 0 here for z, after you get, once you've used the variable, you can zero it out. So you have y equals 2. So it goes from 0 to 2, and then x is going from 0 to 1. And so we're starting with z. So I skipped a step here. But the antiderivative of z, of course, is 1/2 z squared. So I went ahead and just don't have to rewrite the entire thing again. I put the 2 minus y directly in there. So that's the z squared right there. But now it's just going to be 2 minus y squared. And then the 1/2 on the outside, dy dx. Now, it looks like I chose to expand this, but I could have used U substitution. I think either way is fine here. Maybe U sub would have been better. Square kind of left me. Obviously, if it's third power or higher, there's no question you would use U substitution just for the less work, much less work. But I just squared the binomial, which would be 4 minus 4y plus y squared. So the antiderivative of 4 would be 4y. The antiderivative of 4y squared, 4y, not 4y squared, 4y with a negative, of course, and then that would be 2y squared, and then y squared has an antiderivative of 1/3 y cubed. All right, so let's see. So now we just plug in, the rest it's kind of arithmetic here. There's no variable to integrate for x other than dx, so that'll be easy. Put in 2, 4 times 2 is 8, minus 2 times 2 squared, which is 8. And then put in 2 plus 8/3, so these 8s will cancel. And then you have 1/2 times 8/3, which is 4/3. And then the antiderivative of dx will be x. And we put in 0, we put in 1, we'd get 4/3. So it's answer A. All right, another triple integral. Looks like I went ahead and just for the heck of it, put this one in maple just to make sure answer was right. So this one's already set up. So the last one we had to sort of set up the integral. This one we don't. Just kind of have to go through the mechanics of grinding this out here. So obviously, especially all this simplification, use a calculator to simplify. Well, I'll probably skip this simplification at the end. You can send me a message if you want to ask any questions. But really, if you get to this last part right here, you can do the F and N in the calculator if you're using that kind of calculator. If you're not, just integrating it old school, you can, probably get through this, no trouble, but then you just plug in the tube. Let's go back up here and see what's happening. So first one's dx. There's no other x there, so the antiderivative of dx will produce an x, which brings a z and a 5 in there. So obviously that'll make that z minus 5. Now the next integral, well, first I went ahead and distributed this to make it a little easier. So I did distribute. Now we're going to integrate with respect to z. That'll make it a lot less confusing. So the antiderivative of yz squared with respect to z will be yz cubed over 3. And then the antiderivative of 5yz dy will be negative 5yz squared over 2. And then we'll go from negative 1 to y squared. Let's plug those in there. So you put in y squared. Y squared cubed will be y to the 6th. So you multiply those together, and that's where the y to the 7th is coming from. And then right here, y squared squared will be y to the 4th times that y makes y to the 5th. And then you put in negative 1, so it just changes. So negative 1 goes in for z, so it makes it negative y over 3. Negative 1 goes in for the z here, makes that positive 1, so it leaves it negative right there. So it'd be negative 5y over 2, like so. Of course, the negative sign right here is going to change both those negatives to positive. So like I said, this is where you decide if you're using the sort of a TI, whatever, 84 or something like that, or you can take care of the numerical answer from there. If not, it's not too difficult to do this. They're all just basic power rules, so they're not that hard. Or at least, if you're not using a TI-84, hopefully it's got some kind of scientific thing that will take care of the fractions for you or something just to save you some time. It's not that hard, but I went ahead and worked them all out and got denominator, and there we go, negative 31 over 3, but I'm not too worried about you having to mess with all the fractions just from a time standpoint. And there we have it, negative 31 over 3, which is what Maple showed us. And the answer choice was there. All right. So let's see, we got D be the region bounded below by the xy plane and above by the sphere. And then on the sides, we have cylinders. Now this, I should have copied maybe a picture from my notes, but if you go back and look at the notes, we did this kind of problem where it was a cylinder inside of a sphere. So when you're looking downward on it in 2 dimensions, setting up the region of integration, they're both going to be circles on the xy plane. And it says above by the sphere and on the sides by the cylinder. So we are, because there's 2 different ways you can do this. You can have it be, in other words, we did problems where it was outside, it was the region that was outside the cylinder but inside the sphere. But this one's inside the cylinder, and then the sphere curves off the top of it. And that's what we're looking for here. Let's see. I decided to pause the video and open my notes to kind of show you what we're looking at. I'm not saying these are not the same dimensions as our problem, but the idea is the same. So this, like I said, we've had problems where we figured out the volume, outside like this. But we are not doing that today. this problem, we are actually figuring out the volume in here. Now, don't let the fact that this, so even though this picture, just the way the dimensions are, shows this cylinder going through the sphere, our upper limit is the top of that rounded sphere, chopping it right off there. So we're inside the cylinder, but here's, like there's, on a plane, XY plane, they're both circles. So you can tell pretty easily here then that if you look at the dimensions, see that's the sphere has a radius 6 and the cylinder has a radius 4. So obviously the sphere is outside the cylinder. So let's see what we have. It's just asking to set this up. Now we have to look at we're looking at the Z first, so you see obviously the R, dZ, dr, d theta is the same answer for all of them, so obviously the only difference is the limits. So we have to set up Z, which Z will be in terms of R. The height is some sort of function of the radius. It's not a constant radius, but it's a function of the radius. And the height is determined, so you just take basically take the sphere equation and you replace x squared plus y squared with r squared and then solve for z. So then obviously just the upper part. So z would equal the square root of 36 minus r squared. So the height's going from 0 to the square root of 36 minus r squared. And our radius is going from 0 to 4. And then there's nothing restricting it from going around the entire cylinder slash sphere. So there's 0 to 2 pi, nothing keeping it trapped in any quadrant or anything like that. So, and then there you have it. And it was just asking for a setup, but this integral would not have been that bad to work out, because as soon as you dropped, did the z, throw the z, you would throw this radical in there. And then it would just be U substitution with a square root in there. Wouldn't have been that bad. In fact, I'll go back over to the... Of course, it's going to have some sort of square root type answer there, but... Yes, you see the U to the 1/2 right there, so... Wouldn't have been too gruesome. So let's come down here to 62. Volume of a tetrahedron cut from the first octant. Tetrahedron is basically, let me scroll back up here to this other problem we did earlier. It's like this right here. It's this triangle thing cut out like the volume of that kind of wedge of that triangle cut in the first octant. So it's quite all right if you don't know that word. So here we go. Now it's telling you dx, dy, dz, because obviously there's 6 possible orders of integration that would work for this, but we're only looking for one of them here. So if dx is first, that means I have to solve for x in terms of y and z. That's how we determine that. So then, I wrote this equation out, got rid of the fractions by multiplying everything over 60. So by 60, excuse me, not over 60, but by 60 to clear out the fractions. I guess, let's see. So from there, I'm solving for x. So move the y and the z over. And I divided by 20. Well, mathematically this is correct, what I have right here, but to make it match the answer, I went ahead and, distributed the 120 through there. And then it's 3, and then 12 over 20 is 3/5, and then minus 15 over 20, which is 3 over 4 z. Of course, that's also correct, but to match the answer, it needs the 3 factored out of there. So we narrowed it down to either C or D here, so the 3 is just factored out. So it's just that's the way they chose to do it. It wasn't necessarily one way better than the other, but they did pull the 3 out, so we had to do that. So now to solve for the YZ plane for the outer two limits, we get rid of the X is gone, so you can take the equation and replace 0 for X, and now look at it strictly in terms of Y and Z. Now, instead of going back to the original, I just went to this equation right here. Since that's what, X equals this, so X will be 0. And then we have this equation, got rid of the fractions, solve for Y in terms of Z. So that'll be my middle limits. And then divide by 12, which gives you 5 minus 5/4 Z. Okay, they got cute there and factored out the 5 from this. There's nothing wrong with this, but to match that, it needs the 5 factored out. And then to get the outer limits of integration, you basically zero out the X and the Y. So if I go right back up here, I'll just go right to this one. I know I use this, but I'll go right back up here, put in 0 for X, 0 for Y, 15Z equals 60. So we know that Z equals 4. And then there's the setup. So it was answer C. Now there's a very, very similar type problem where it's asking us to change the order. Let's see if the last one we were just given the equation, it told us an order. Now it's giving us an integral in a specific order. Can we rewrite it to another order? So once we get the original equation back, then we'll do the similar process we did to the last one. So since we know that dx is on the inside in the original, I know that x will equal that upper limit. So if x equals that upper limit, so x equals all this stuff, multiply, just do a little simple algebra there, and you'll come up with this basic equation of the plane right there is x plus 5y plus 2z equals 10. Which gives me now, I want dz, dy, dx. That's the order it's telling us. So that means that's how I know I want to solve for z first. So you take this equation, move the x and 5y over and make them negative. Solve for 2z. So z will equal 1/2 10 minus x minus 5y. Which it looks like they did the crazy factoring out 5 thing again. Kind of weird, but well, you could always, if you thought you knew which answer it was, you can distribute their answer and distribute this answer and see what matches. So basically, to get it to match the inside limits, 1/2 to factor the 5 out. 1/2 had to be converted to 5 over 10. So that way, because that way 5 over 10 right here makes it 1/2. So we have 0. So I guess that's it right there. Once you have that one, that gives the answer away then, doesn't it? But let's see, I'm sure I did quit there, didn't I? Well, I guess I should have kept going, but I'll sort of explain verbally here what happens. And the next one, you would zero out the z because it's not being used anymore, so then z would be 0. And then because y is next, I'd solve for y in terms of the rest of everything else. So if I move the minus 5y over, I'd have 5y equals 10 minus x, which divide both sides by 5. And I have 5y, 10 minus 1/5. So it's 2 over x minus 5. And then you got to get the common denominator, 2 minus x over 5. But then they did the 2 factored out, so they had to make that x over 10. And then the last one, for x, you would zero out y and z, and therefore you have x equals 10. So it's 0 to 10 right there. So, okay. Sorry I didn't finish all that out, but I think so it did work similar to the last problem, the remaining steps, if you want to try to finish it yourself. And now we have a spherical coordinate integral that we are just evaluating. We're not setting it up or anything. We're literally just working it out as is. So you don't add any, I know when you convert to spherical, you always add, rho squared sine phi, or phi, whatever it's called. But this one, you're just integrating it as is. So rho is the first integral, so rho squared d rho would make it 1/3 rho cubed. Oop, don't want that. And then we're plugging in 2 cosine phi. Already have a sine of phi. So you plug in 2 cosine phi into rho cubed. That gives you 8 cosine cubed. So I just brought the 8 to the outside. Then you see the cosine cubed is still there. A phi, sine phi. D phi, d theta, d phi. Sorry if I'm pronouncing that wrong. Now be careful with some of these problems in the sense that I'm not sure this is going to necessarily happen to you on the final, but sometimes people will confuse the phi and the theta. They'll think it's the same variable, So obviously if that was cosine cube phi sine theta, you would not do what I'm about to do right here. But since they're both the same variable, yeah. It's just u substitution, so it's pretty straightforward. Cal 1 type integral. I'd let u be cosine. The derivative will be negative sine phi, d phi. Put in pi over 2. Cosine of pi over 2 is 0. Cosine of 0 is 1. So pull the negative out. So it's negative 8/3. 0 to pi over 2. 1 on bottom, 0 on top. And I just have u cubed du d theta. Now I did the same thing here that I've mentioned in a couple of other ones, where I just used the property where I reverse the limits of integration. So changing that 0, 1, 1 on bottom, 0 on top, to now 0 on bottom, 1 on top, gets rid of the negative. So there's no negative there. So we have, let's see. All right, what do we have here? So we have antiderivative of u cubed is u to the 4 over 4. That's what happened to the 8, because it'd be 1/4 u to the 4th. So 1/4 times 8/3 is 2/3. So I just didn't show that step because it wasn't a, just a kind of a basic antiderivative. But yeah, so you might wonder how the 8 turned into the 2. It's from the 4 in the denominator of this antiderivative. Put in 1, put in 0, that just turns into 1. Now you're left with d theta. So 2/3, 0 to pi over 2 d theta, just throws the theta in there. So it just tosses a pi over 2 in there. So 2/3 times pi over 2 would just be pi over 3.